Hi, we're going to talk about 2.7, polynomial and rational inequalities. So in the first half of chapter 2, 2.1 to 2.5, we talked about graphing polynomial equations, functions. In 2.6, we talked about graphing rational equations. And now in 2.7, we're going to put those together, and we're going to talk about graphing polynomial and rational inequalities. Okay, so objective 1, polynomial, objective 2, rational, and objective 3. I'm going to give you a taste of some applied problems that might involve specifically polynomial here. All right, so you have this procedure box, this step-by-step, this 5-step strategy for solving polynomial inequalities. Just like I did in 2.6 with graphing rational functions, they gave you a 7-step process, and I cut that down to 3. I'm going to put my perspective on this 5-step table. Okay? All right, so I'm going to go through example 1 with you. Objective 1 is solve polynomial inequalities, and we're given this equation 2x squared plus x is greater than 15. Okay, so the first thing I want us to think about is, what is this really asking us? Okay, before we get to the algebra of solving it that way. So, what is this really asking us? This is really asking what x values, that's the missing variable, so what x values make 2x squared plus x greater than 15? That's what this is asking us. Okay, so there's 2x squared plus x greater than 15. And we can look at a graph to help us see that. So what I've done is I have graphed in blue the y equals 2x squared plus x and what that parabola looks like. In the green, I have graphed the y equals 15 and what that parabola looks like. And as far as what x values make it greater, greater in this case means above. So you should be able to see that back here before we get to this intersection point. So back here, this arrowed kind of ray, these would be the points that are greater than 15. And then these would be the points on this side of the parabola that are greater than 15. The intersection points specifically are negative 315 is the intersection point on that side, and 2.5, 15 is on the other side. I'm going to be talking to you about exactly how I found those two algebraically here in a minute. Okay, so let's go ahead and get to that. And I'll show you how to write your answer as a solution set here in a little bit. So if we're going to solve this algebraically, which is what you need to be able to do, before we find the greater than 15 for 2x squared plus x, we have to find the equals 15. Okay, so we're going to set this up as a quadratic equation, and we're going to solve it like we would a quadratic equation. Okay, so we're going to make it equal 0. We're going to factor. We're going to set each factor equal to 0. So remember on the previous page, I had 2.5. That's what 5 halves is, and an x value of negative 3. So these two x values were those 2 points of intersection. Okay, so if we're going to graph, if we're going to think about how to solve this, the 2x squared plus x equals 15. That equation has zeros at x equals negative 3 and x equals 2.5. Okay, we're going to be building this graph as we go. All right, so step 1 is find the zeros. And then step 2, we're going to test values between the zeros and beyond the zeros. And here's what I mean by that. We need to pick an x value that lies somewhere between, in this case, negative 3 and 2.5. Okay, and whenever I can pick an x value of 0, I do. Okay, 0 followed closely by 1. Those are my favorite substitutes. So we are going to test this in the original equation, the 2x squared plus x is greater than 15. And we need to see if this is really true. So 0 greater than 15, no, it's not. So what that tells me is none of these x's in this region between the zeros will satisfy that inequality. Now let's test the ones beyond. And by beyond, I mean on this side. Make a little arrow there. Okay, we're going to do that one first. And if we're going to test these values over here, we're going to pick an x value that lies somewhere on this arrow. I chose -4. Okay. Testing -4, 2 times -4 squared plus -4, is that really greater than 15? Well, 28 is greater than 15. So that's a green check mark right there. That means that the x values included on this arrow are part of our solution set. Now we have one more beyond region to check, and that's this region over here. Okay, so we need to check an x value that lies on this right side. And I chose +4. 2 times 4 squared plus 4, is that greater than 15? Well, 36 is greater than 15. Okay, so the reason that these two were checked and this one was not was because this statement is false. 0 is not. I'm going to try to do a slash. 0 is not greater than 15. Okay, so step 1 was find the zeros. Step 2 was let's do some test values. And in step 3, we are going to be writing the solution set. Before we do that, I want to show you graphically an alternative to the test points, okay? So if we think about this as the 2x squared plus x minus 15, and we already plotted the zeros back a couple slides ago, if we think about end behavior, I want you to think about for a second, should this cup up or cup down? Okay, so we have this cupping up. If we use this, we are asking what x values make the parabola greater than 0 this time because we moved the 15 over. So you can see the green is the area where this is greater than or above 0. So the x values that go with that would be these over here and these back here. Okay, that should look familiar to you. Either way, you can find them with the test points that identifies this region, the x values less than -3, the x values greater than 2.5, or you can use the graph to say we need the two pieces that are above the x-axis, so that's going to be greater than 2.5, less than -3. And that's the solution set. Here's the solution set in set builder notation. The set of all x values such that the x's are less than -3 or the x's are greater than 2.5. In interval notation, we have two intervals to show the two separate arrows. -infinity up to -3, and then join with that with the union symbol, 2.5 to +infinity. We do not have the square brackets on those because this was not a greater than or equal to problem. It was just a greater than problem. Okay, I want to show you really quickly, what if this had been a less than equation instead of a greater than? So I'm just going to go with the graphic really quickly. If we'd been looking at less than, instead of going for these parts that are above out here, we would be looking at this segment that is below and matching the x values that would go with that segment. That would mean from the test points that the numbers between the zeros would work, but beyond the zeros would not work. And that solution set would be, if this had been the problem, that solution set would be the x values between -3 and 2.5. And then there's the interval notation. Again, no square brackets because we don't have an or equal to in this problem. Okay, now let's go to rational inequalities. What you might want to do at this point is pause and go to your Math Excel assignment for 2-7 and start to work on those. The first few will be polynomial inequalities. So you can go and work those now and then come back and pick up here at 10 minutes and 40 seconds to see my example with rational inequalities. Okay, so with this rational inequality, I want you to remember this is with objective 2 in your textbook. What is this really asking? Well, it's really asking, where is this rational function greater than or equal to 2? So again, I've graphed that so we can see this. Here is the line y equals 2. That's that line right there. And then the blue is the x plus 1 over x plus 3. It's that line. We want to know where the curve is above 2. And so you should be able to see it's this piece right here. Okay, graphically, that's where it's above 2. Let's see how we can find this intersection point exactly and get the solution set. The process is going to be very much the same as the polynomial. So before we find the greater than or equal to 2, we have to find the equal to 2. Okay, so we're going to set our equation equal to 2. And if you're seeing a proportion here, you're on the right track. We're going to solve this by multiplying the x plus 3 up and then working through the dotted arrow. I'm trying to indicate to you that there may be some inner work steps that you need to do to make sure you answer this correctly. Eventually, you should get to where x is equal to -5. Okay? If you glance back at this graph, if we were to zoom in a little bit, we should see that here's -5 and there's that intersection. So the algebra is confirming what we thought from the graph. Okay? Now we also have to keep in mind any excluded values. That's going to be a trick with the rational inequalities that we did not have with the polynomial. So the excluded values, remember we need to know what can x not be, and x cannot be -3. Okay, so that's going to come into play when we do the test points next. All right, so we are going to test x values between and beyond the zeros and the vertical asymptotes. So I have the vertical asymptote here where x is -3. I have the x-intercept plotted at x equals -5. To test a value between, that would be the -4. And I have the fraction written like this only because the program isn't letting me do the horizontal fraction bar. We're asking, is f of -4 really greater than or equal to 2? And 3, yes, is greater than or equal to 2. So we know that if -4 worked, then any value here in this middle section between -5 and -3 will satisfy. If you don't believe me, pick a number other than -4 that's between -3 and -5. Maybe like -3.5 or -4.9. Test me on it. We also need to test the points beyond the zeros and the vertical asymptotes. So back here, guess which one I picked? -6. And if you test that, we get 5/3. Now, is 5 over 3 greater than or equal to 2? You can check this on your calculator if you need to. Change it into a mixed number in your mind. How many times does 3 go into 5? Only once. Not greater than 2. So these x values back here are not above the 2. They're actually below when we calculate the y. We need to check on the other side of our vertical asymptote. So something over here, and my favorite, 0, I'm going to plug in anytime I can. Okay, so is this greater than or equal to 2? 1/3 is not greater than or equal to 2. So we know nothing over here is involved in the solution set. It's matching up with what we saw from the graph in the first slide. Back here didn't work. Over here didn't work. It was only this piece in the middle where the graph was above. Okay, so now we have to write the solution set. And I've shown this graphic over here, again with the multicolor. The blue is not above. The blue is below. The red piece is above. So the between is x's are between -5 and -3. Here's the -5, here's the -3. You might be noticing that I have the or equal to here. That's because in the original problem it said greater than or equal to 2. So if x is -5, that's the equal. And then if we go in this direction, that's the greater. Okay? So why does this one not have the equal to? Well, remember where this number came from. This x equals -3 was the excluded value. X cannot be -3 or the original function doesn't work. So we can never have, just like we're never going to have a closed bracket, a square bracket on infinity, we are never going to have an equal to on an asymptote. In the interval notation, it would be from -5 to -3, including the -5, not including the -3. Okay, just one other thing that I have to show you, and this is, I wanted to take a second to explain a function that we saw last year in Algebra 2, but just making sure we're all good with the V0 and the S0 for this free-falling object function, okay? So S of t is actually the object's height or its position above the ground. Okay, at a certain time. Any position, any height could be modeled by this -16t squared plus, I say this, V0 t plus S0. Okay, naught is a word that means nothing or 0. Like the expression, it was all for naught. Okay. So -16 is what is half of Earth's gravitational constant if we're measuring in feet per second squared, and that's what we have here. The V0 is the initial velocity. So if it says it was thrown upward with a velocity of 10 feet per second, then 10 is your V0. If it said down, then that velocity would be negative if it was thrown down. The initial height is your S0, okay, and that's what goes back here. So if the person was 10 feet off of the ground and that's when they threw it, S0 would be 10. Okay, I think you have everything you need now to be able to do the 2-7 Math Excel homework.